welcome to the Facility for Rare Isotope Beams, or FRIB. This public talk is part of an initiative at FRIB called the Advanced Studies Gateway. The purpose of the Advanced Studies Gateway is to inspire people. We bring together researchers, innovators, creative thinkers, artists, and performers from all different fields, and we build ties between Michigan State University and the community. And today we're delighted to have Professor David DeMille present a talk on quantum microscopes to search for new elementary particles and forces. Professor DeMille is a professor in the Department of Physics and Astronomy at Johns Hopkins University. He also holds positions as a research professor in the Department of Physics at the University of Chicago and as a visiting scholar in the physics division at Oregon National Laboratory. Professor DeMille's research seeks to investigate the fundamental properties of the universe by making extremely precise measurements of quantum systems. He is known for novel approaches that use the properties of molecules to amplify signals from exotic particles and forces in the laboratory, and for developing ways to produce and trap ultra-cooled gases of polar molecules. He received his PhD in physics from the University of California at Berkeley in 1994. He previously served on the faculties of Yale University and Amherst College. He co-authored the textbook Atomic Physics, an Exploration Through Problems and Solutions. His honors include the American Physical Society's Norman F. Ramsey Prize and the Francis M. Pipkin Award. He's also the recipient of a Sloan Fellowship, a Sloan Foundation Fellowship, and a Packard Foundation Fellowship. Professor DeMille was elected a member of the National Academy of Sciences in 2024. Now, at this time, please join me in welcoming Professor DeMille.
Thank you for the very nice introduction, Dean, and it's a real pleasure to be here. I've had the chance to spend a couple of days visiting folks here at FRIB in Michigan State, and it's really been a fantastic visit. I'm going to be telling you today a bit of a story about how to look for new particles and forces in an unusual way, a way that doesn't require gigantic facilities, but instead can be done in rooms that are, maybe a third or a quarter the size of this room, with just a handful of young scientists and a couple of old people like me, getting in the way, which we think is very exciting, and maybe even the best way to look for new fundamental particles and forces in the coming few decades. So, let me start with telling you how particle physicists like me look at the world. How do we think about what's happening in the world, the universe at large? And a place to start is, what we learn in high school and even middle school is that the world is made of atoms. Atoms are made of electrons, and they have a nucleus which is made of protons and neutrons. And maybe in high school, certainly if you make it into a college physics course, you learn that protons and neutrons are not really elementary particles. They're made up of quarks. Protons are made up of two up quarks and a down quark. Neutrons are made of two down quarks and an up quark. But our current understanding of particle physics is that electrons, up quark and down quarks, are really fundamental things. There's nothing smaller inside of them. So this is what the world is made of in many ways, is electrons, up quarks and down quarks, at least the world that we usually see in ordinary life. But over the course of the 20th century, it was understood that there are additional particles which are mostly closely analogous to electrons, up quarks and down quarks. So, for example, in addition to electrons, there are other particles called muons and tau particles that are in many ways very similar to electrons, only heavier. And it's kind of a mystery why these exist. There's a famous quote from a particle physicist saying, "Who ordered this?" But we know that the world can contain these things. We don't see them very often because they decay very quickly. But they've been observed. We know they exist. And likewise, in addition to up and down quarks, there are heavier quarks that have very fanciful names. Charm quarks, strange quarks, top and bottom quarks, that are very, very similar to up and down quarks, but heavier, and they decay very quickly, so we don't see them in the ordinary world. There are additionally particles called neutrinos, which are stable, they don't decay, but they interact with the world very, very feebly. They're actually around us all the time, but because they interact with us so weakly, we don't notice their presence. But from the particle physicist's point of view, the universe is really made up of not just electrons and up and down quarks, but all of these types of particles. The types on the left here, including the electron, are called leptons, and then all the various types of quarks. But in addition to knowing what the world is made of, we need to know how the pieces of the world interact with each other. And according to our current understanding, there are 4 fundamental kinds of forces, ways that the different particles, the leptons and the quarks, can interact with each other. Those 4 forces are gravity. Of course, that's very familiar from the ordinary world. There's electromagnetism, and that's fairly familiar. Everyone's been shocked by a spark of static electricity in the winter. Everybody's held a magnet and seen it grab onto the steel in your refrigerator door. Things that are a little less familiar are what's known as the strong force. This is the force that holds protons and neutrons together inside a nucleus. And you can tell that something has to be going on inside a nucleus like this, because the electromagnetic force will cause protons that both have positive charges to repel from each other. So something has to hold them together, and that something is called the strong force. And it's called the strong force because it's much stronger than electromagnetism. It's strong enough to overcome the electric repulsion between protons in a nucleus. Then finally, something that is less familiar from ordinary life, known as the weak force, is responsible for a few different things. In particular, it's responsible for certain kinds of radioactive decays. For example, if you have a neutron just sitting by itself out with nothing around it, within a couple of minutes it will decay into a proton, an electron, and an electron neutrino, or more specifically, an electron antineutrino. And none of the other forces can cause that to happen. There's an additional force needed to explain that that's called the weak force. So that's a little more complicated than we're used to from ordinary life, but there are only 4 of these forces. There's not dozens of them. So from the particle physicist's point of view, the way we think about the forces, the various forces between particles, is that they are carried by additional particles. So for example, the electromagnetic force can be described from the particle physics point of view as due to charged particles tossing back and forth new particles called photons. These are particles that carry the electromagnetic force. The weak force is carried by different particles called W and Z bosons. The strong force is carried by yet more particles called gluons. And gravity, well, we don't actually know what that's carried by. We think it should be carried by particles called gravitons, but there's no actual evidence for that yet. So the way that we understand both particles, the particles that make up matter, quarks, electrons, leptons, neutrinos, and the particles that carry forces like photons and gluons and W bosons, is that in some sense they're particles, but in the language of quantum mechanics, and in particular quantum field theory, which is the mathematics that describes how particles interact with each other, is that these particles are associated with something called a field. And what is a field? Well, it's a sort of, it's a thing that you can imagine as some entity that fills all the space in the universe. And it's a little hard to visualize, but so let's imagine the universe, instead of being 3 dimensions, was 2-dimensional. It was just a flat sheet. Then you can think of these fields as every type of particle. For example, electrons have a field that fills all of 2-dimensional space. And what an electron particle is a little bump, a little excitation in the electron field. And that bump can move around, sort of like if you imagine this as being a drum head. If you manage to yank up on a drum head, get a little bump, that bump will bounce around on the drum. And this is, in the language of particle physics, the electron particle is a little bump in the electron field. And that electron field is everywhere in the universe. That little bump can move around, and that's what we call an electron. You can also have, instead of a little bump, a little dent in the electron field. And that's how particle physicists think of the antimatter counterpart of the electron, the anti-electron, also known as the positron. So particles, in the language of quantum field theory, are actually little bumps in these fields that are traveling around. And according to the standard model, or according to our current understanding, the universe is filled with lots of different kinds of fields. One different field for every kind of particle that can exist. The electron field, the photon field, the up quark field, and so on. The Higgs boson field. Every kind of particle that exists is associated with a field that's everywhere in space all the time. So the way that we've understood the kinds of particles that exist in nature, that can exist in nature, is really based on Einstein's principle that E equals mc squared. Energy is equal to mass times a number, which is the speed of light squared. What this equation E equals mc squared really tells us is that energy and mass are equivalent to each other in a very fundamental way. And what that equivalence means is that it's possible to turn energy, for example, in the form of 2 photons, each of which has 0 mass, colliding with each other, and the energy of the 2 photons can be converted into 2 particles, for example, an electron and an anti-electron. Or vice versa, if an electron and an anti-electron collide with each other, they can annihilate and turn back into pure energy in the form of massless photons. So the traditional way of studying particle physics, or of understanding particles, is to create new particles by converting energy into those new particles. And I'll just mention that, as I've shown in these examples, though there are many other examples, energy can turn into not just electrons and anti-electrons, but protons and antiprotons, quarks and antiquarks. But according to our understanding, every time energy converts into mass, equal numbers of particles and antimatter counterpart particles have to be made. So particles and antiparticles have to be made and destroyed together in pairs. So, we can sum up what we know about particle physics really in one slide. It's a kind of complicated slide, but essentially what we know about particle physics is that there are the particles that have mass that I talked about before, the quarks and the leptons. There are the particles that carry forces, the gluon and the photon that have no mass, and then the additional particles that carry the weak force, the W boson and the Z boson, which do have mass. And then there's the last piece of the Standard Model, the Higgs boson, which was discovered about 10 years ago, which also carries certain kinds of forces. So the Standard Model of particle physics really consists of two parts. It's this catalog of what are the kinds of particles that exist. And again, each of these particles is associated with a quantum field that fills all the space. And the particles are little excitations of their own particular quantum fields. So in addition to this catalog of the kinds of particles that exist in nature, there's some equations that describe how these particles interact with each other, and essentially how they behave. This Standard Model of particle physics it's really, I think, one of the pinnacles of human achievements. So this catalog of what exists and the equations describing how the things that exist interact with each other, what are their properties. It was a mathematical framework that was put together back in the 1970s. And over time since then, everything that's been predicted about the behavior of particles in the laboratory by this mathematical framework, within this mathematical framework, has been verified. Everything it predicted has been seen. Everything that it's been seen in the laboratory is consistent with this mathematical framework. It's really quite remarkable. It predicted the existence of several particles like the Z boson and the W boson before they were observed. It predicted the existence of the Higgs boson and of the top quark before they were observed. And it predicted many, many different properties of these particles, often with extremely high precision. And and every piece of the Standard Model that was predicted has now been observed. So it's a completed theory of nature. But we know that it's not the full theory of nature, that it's a self-consistent mathematical framework that describes what we've seen in the laboratory, but we know that it doesn't describe everything that exists in the universe. And we know this mostly from astrophysical observations. So we know, for example, that there's something that we call dark matter, some substance that acts to bind together the stars and galaxies through gravitational forces. And we know that none of the particles in the Standard Model have the right properties to act as this substance that we call dark matter. There's something different that's not in the Standard Model of particle physics that must exist. There's an additional mystery of the Standard Model, which is that, as I mentioned before, when energy is converted into particles that have mass, that conversion process has to produce equal numbers of particles and antimatter particles. So after the Big Bang, the gigantic energy of the Big Bang could be converted into particles that have mass. And when that happened, the Standard Model says equal numbers of particles and antimatter particles should have been created. The trouble is, when we look out in the universe now, we see essentially no antimatter particles. We actually see that most of the energy of the Big Bang is still in the form of energy. Some tiny fraction, about 1 part in billion of the energy of the Big Bang, has been converted into particles that have mass, electrons, up quarks, down quarks, and essentially none of it has turned into antimatter particles. And this is a giant mystery. According to the standard model of particle physics, there should have been equal amounts of matter and antimatter, and either there should be equal amounts remaining now, or they should have all come together and annihilated back into pure energy. And apparently most of them did come back together and annihilate into pure energy. But some tiny fraction has survived in the form of matter that forms everything around us, everything we know, stars, galaxies, people, puppies. So we don't know how that can be. Both of these observations about the universe are telling us that there have to be additional particles, additional forces, additional quantum fields beyond what is described in the standard model. And there are other phenomena that are even more mysterious, such as dark energy, but I won't go into that. Yeah.
So is the problem of neutrino mass also expanded by the Higgs boson interaction within the framework of SEMR, or is it something?
Yeah, so this is, I would say, there are different opinions about this. My own opinion is that it's possible to describe neutrino mass in the framework of the standard model by assuming that neutrinos interact with Higgs bosons in the same way as other leptons. It wasn't built into the original structure of the standard model because at the time people thought neutrinos might have actual zero mass. And there are good reasons to think neutrinos may get mass in some different way, but it's entirely possible that neutrinos get mass in the same way as other leptons. And for me, Occam's razor says I'm going to tend to believe that until there's evidence otherwise. So, from the point of view of a particle physicist, the real question is, what comes next? We know that there have to be new particles, new forces, new quantum fields beyond the ones in the standard model described in this cartoon, all the particles and the rule book of how they interact with each other. But there must be some new rule book, or an appendix at least to the existing rule book, and some kind of new particles, new quantum fields. But the big question in the field is, where are they? What are they? What do they act like? How can we find them? So the obvious answer is, let's make them. Let's go and make them. And the latest attempt to do this is the famous experiment at CERN in Geneva, Switzerland, called the Large Hadron Collider. And it's indeed large. It's an accelerator with a ring with a diameter of almost 10 kilometers, where protons are accelerated around the ring in opposite directions. At a few places, the rings cross. The protons that have been accelerated to have enormous kinetic energy collide with each other. That kinetic energy of the collision can turn into new particles if the energy of the collision is at least as high as the mass of the particles times c squared. So, for example, one of the things that people thought they might see at the Large Hadron Collider is two of the gluons that are inside protons colliding with each other to form some new particles called T leptoquarks that would then decay into ordinary particles that could be detected. This is one of the detectors at the Large Hadron Collider, and if you can see right here is a human. So these are absolutely gigantic detectors, the size almost of an entire building, with thousands of people working in parallel to make the experiments run and to detect the particles. And after the discovery of the Higgs boson, it was really widely expected that the Large Hadron Collider would make some sort of new particles beyond the ones in the Standard Model, and there would be much rejoicing. But alas, that's not been true. Nothing outside the Standard Model has been observed at the Large Hadron Collider, which is the highest energy accelerator in the world, and the one with the best chance to see new particles with masses higher than anything that's been possible to detect until now. So the LHC continues to run. There's still, some hope that they will be able to uncover new particles, but it's not clear that they will. So what we're doing is an alternative way to look for new particles, taking into account the fact that the particles are not just particles, but are actually also associated with quantum fields. And one of the properties of quantum fields that is different from just particles that look like billiard balls is that the quantum field can have what are called virtual excitations, where instead of having a bump that moves around that looks like an electron, for example, you can have, for very brief periods of time, you can have bumps that appear and then disappear. Even when there's not enough energy to create a particle, you can, for very brief periods of time, have little bumps appear and then disappear. And those bumps that are only present for short periods of time and then disappear again are called virtual particles. And this may seem mysterious because if you just have a quantum field here having zero energy, in order to make, for example, an electron and an anti-electron, E equals mc squared says you need some energy to make those particles that have some mass. But in quantum mechanics, the uncertainty principle tells us that it's possible to sort of spontaneously appear to have energy for very brief periods of time, so long as the amount of energy that appears temporarily times the short amount of time that it appears is less than Planck's constant over 2. And in fact, the electromagnetic force, let's say between two electrons that are repelling from each other, or between an electron and a proton in an atom, can be thought of as being carried not by real photons that have energy, but by virtual photons that are sort of blinking in and out of existence very rapidly. And I just want to emphasize that the fact that space is filled with these quantum fields everywhere all the time. Those quantum fields are not just static things. They're constantly, all of those fields have virtual particles popping in and out of existence everywhere all the time. So what we call the quantum vacuum, which is empty space, is not really empty. It's filled with these quantum fields, and those quantum fields are fluctuating, creating virtual particles everywhere all the time. So empty space in quantum field theories is actually a complex and dynamic environment. And this is a nice illustration. So I told you that protons are made of 2 up quarks and a down quark. But in fact, inside a proton, there are virtual gluons holding the whole thing together, appearing and disappearing all the time. There are also virtual quark and antiquark pairs virtually appearing and disappearing all the time. And this is a movie that's made of an actual calculation of the gluon fields inside a proton and how they're constantly sort of bubbling bubbling around everywhere all the time. So the way that I'm going to describe to do particle physics is essentially trying to see evidence of new particles through how they fluctuate in empty space. So this is actually a time-honored way to look for new particles. So way back in the 1950s, the phenomenon of radioactive decay was observed. And it was understood, very, very early on, that the new force, the weak force that was needed to describe these radioactive decays, had to be associated with some sort of new particle carrying that weak force. And it was called the W particle, because it's a weak force. Get it? So it was understood for decades that there should be some new particle associated with a weak force, carrying the weak force, the W particle. But it was only in the early 1980s that colliders with high enough energy to convert that energy into the particle, the W particle, which is very, very high mass. Only in the 80s did that become possible, and was the W particle directly observed. But already decades before, it was possible to know that there would be such a particle. And there are other examples of that. For example, when the standard model of particle theory was constructed in the early to mid 1970s, one of its predictions was that the weak force would have with it not only particles, the W particles that are responsible for radioactive decays, but an additional force-carrying particle that was named the Z particle that would carry a weak force that didn't cause things to decay necessarily, but for example, would always be present, being carried virtually back and forth between electrons and neutrons and protons inside a nucleus, along with the virtual photons that carry the electromagnetic force that holds atoms together. And it was predicted in the standard model that these Z bosons would have a very peculiar property, which is they would cause the electrons in an atom to travel not in circular orbits, but in these very funny helical orbits, so that they're constantly going around, but then winding around in a trajectory sort of like this. And if you stare at this, you realize that this picture has a funny feature, which is that as the electron goes around, if I wrap my fingers around the direction that the net flow goes, like this, my thumb points out of the page. But if I do that with my left hand, my thumb points into the page. So this thing is like a right-handed picture, and a left-handed picture would look different. The weak force carried by the Z boson is the only force in nature that can cause atoms to have this sort of twisted handed structure. And it's really kind of amazing. It turns out that if you take light, polarized light, and shine it through a gas of atoms, if the light comes in with a polarization in this direction, when it comes out the other side of the atoms, the polarization will have rotated by some amount. And it will have rotated by a direction that can be predicted by the standard model of particle physics, by a direction and an amount. And you might say, well, why doesn't it rotate the other way? Who decides which direction it rotates? And the answer is the weak force in the Z boson decides which direction it rotates. And for any given atom in any given wavelength of light, you can predict how much it rotates and which direction. And by measuring those things, you can actually confirm some properties of the Z boson. And that was indeed done very, very soon after the first particle physics discovery of the Z boson. Measurements of the virtual Z bosons and their effect in atoms confirmed what had been seen directly in colliders. So, using that theme, I want to dig in a little bit to how we use virtual particles in our labs recently, and in particular virtual particles that are around electrons, to detect the existence of new particles, new forces, new quantum fields. So the place to start is to tell you, what is an electron. And this is a nice cartoon picture of an electron. An electron is a ball of negative charge. And that ball of negative charge is always spinning. You can't make it stop. It's always spinning. And as it spins, its spin makes it act like a little magnet, as shown here. So this is the picture to keep in mind if you think about what is an electron. It's both an excitation of an electron quantum field, but if you go in and look at what that bump in the quantum field looks like, it looks like a little ball of negative charge that is also a magnet that's spinning all the time. So the electron by itself is a little bump in the electron field, but that electron field is also everywhere all the time in the presence of other quantum fields. The photon field, the Z boson field, the W boson field, the quark field, all the fields, quantum fields are everywhere all the time. So it turns out that as an electron, an excitation in the electron field, or an electron, in other words, moves through the universe, it's constantly interacting with all the other quantum fields that are everywhere all the time. And for example, the electron can virtually excite a photon, virtually emit a photon for a very brief period of time, and then reabsorb it, and then carry on. And as the electron travels, it's constantly spitting out and reabsorbing photons. It's also spitting out and reabsorbing Z bosons and W bosons and every other kind of particle that can exist in nature. It's constantly spitting them out and reabsorbing them as virtual particles. And this was a famous discovery back in the very early days of quantum field theory in the 1950s, that these virtual particles, virtual emission and reabsorption of photons around the electron, modifies the strength of the magnet that's attached to the electron. And you can describe the strength of the magnet of the electron with a number called G. When people first realized electrons were spinning particles and should have magnetic moments, the original theory said G should be exactly equal to 2, but the virtual particles surrounding the electron cause its magnetic moment, its G, to be not 2. So G minus 2 is not 0. And this was a famous prediction of the earliest versions of quantum field theory that was verified already in the 1950s. But this is only the simplest thing that can cause the electron's magnetic moment to be different from 2. Everything that possibly can happen in nature is happening all the time everywhere. So all the time the electron is virtually emitting a W boson. That W boson is virtually splitting into top and bottom quarks. And then the whole thing comes back together and it turns back into an electron. That's happening all the time for very brief periods. These pictures, known as Feynman diagrams, actually correspond to mathematical equations that describe what's happening here. And those mathematical equations say that the heavier the particles that appear in the loops of these pictures, the smaller the effect on the magnetic moment of the electron. mass gets 10 times bigger, the effect is 100 times smaller. And in these pictures, the more loops that you see correspond to smaller and smaller effects. So this is a big effect because the photon is zero mass. This is a very tiny effect because it relies on very massive particles like W bosons and top quarks, and because there are two loops in this effect. So it turns out that in addition to modifying the strength of the magnet that is an electron, virtual particles around the electron can have other effects. And one effect that they can have is to cause the electron to be not a perfect spherical ball of charge, but instead to have a sort of egg shape, or rather the cloud of stuff, the cloud of virtual particles surrounding the electron can carry a charge that's sort of egg-shaped. And the standard model of particle physics predicts that that should happen, predicts that the electron should be not spherical, but a little bit egg-shaped. And the way that that happens is described in this diagram, where the electron virtually emits a W particle that virtually splits into a top and bottom quark pair. The bottom quark virtually splits into a W boson and a different quark. And this stuff all comes back together. The electron temporarily turns into a neutrino. So you can see this process in the standard model is, it has a very tiny effect because it involves extremely heavy particles like W bosons and top quarks. It has 4 loops in this picture, so it's 4th order small. And then it turns out in the standard model of particle physics, there are many different processes described by many different pictures like this. And when you add up all the effects, they largely cancel each other. So in the standard model of particle physics, the electron has this egg shape, but it's almost perfectly spherical. It's really close to perfect sphere. So, as I'll describe, it turns out that other kinds of virtual particles can cause electrons to have bigger, a more deformed shape, less spherical shape than the standard model. So it turns out to be interesting to look for this deformity in the shape of the electron. And this is the way to picture what that looks like. So suppose you have an electron that's a perfectly spherical ball of charge, and you add to it what's called an electric dipole moment. This is basically a little bit of positive charge and a little bit of negative charge that are separated from each other, stuck on the ends of a stick. And suppose that this extra charge, a little extra positive charge, a little extra negative charge, is actually stuck to the electron. So that the positive charge cancels the negative charge up at the top here, causes a little dent. The extra negative charge causes a little bulge at the bottom of the electron. So this is something like an egg-shaped electron. And suppose that the deformation is along the axis the electron is always spinning around. So this is the kind of phenomenon that I just said is known to happen in the standard model of particle physics at an extremely tiny level. But the question is, why is that such a tiny thing? What is it about it that is so odd? And the answer is that if you take a movie of an electron like this and run it backwards in time, do what's known as a time reversal transformation, then when you run the movie backwards in time, you'll see the electron is spinning in the opposite direction. But the shape of the electron doesn't care whether time is running, or the movie's running forward or backward. The shape of the electron will be look the same as it did in the original. So what that tells us is that if all electrons look like this, with this deformed shape, with a little dent along the direction it's spinning, and a little bulge in the opposite direction. Then the time reverse version of that doesn't exist. In physics, we call that a violation of time reversal symmetry. And this is something that's very, very exotic. It's only been seen in a few systems. And it's predicted to occur in the standard model of particle physics, but only in very special situations. Turns out this is quite interesting because it's understood that to explain the matter-antimatter asymmetry in the universe, the standard model, as I said, can't do it. But in order to do it, you need some sort of new forces that violate this time reversal symmetry. Time reversal is closely related to the relation between matter and antimatter, as it turns out. So new forces that violate time reversal symmetry, we know they have to exist in order to explain this matter-antimatter asymmetry. And looking to see if particles like electrons have this funny deformed shape is a way to tell, or a way to look for new forces for that property. Well, you can, this actually has an equation, which is a problem, but here's what you should really take away from this, which is that if there are new particles that mediate new forces that are virtually blinking in and out of existence around an electron, and those forces are the right type of forces to cause the electron to have an asymmetric shape, then our experiments are currently so sensitive that we would be able to see this effect if these new particles had masses of, well, roughly 500 times heavier than the Higgs boson. So this is a way to look for new particles with extremely high masses, much higher than you can see directly even at the largest colliders. And here's a plot that shows this experiments over many decades have been looking to see if electrons have an EDM, an electric dipole moment, which is just a way of describing this asymmetric charge distribution. Over the years, these experiments have looked and been more and more sensitive. So far, none of them have seen a deformed shape of the electron, but they've been able to look for smaller and smaller deformations. Those smaller deformations correspond to what would have been created by higher and higher mass new particles. And the points on this graph show that already current experiments are sensitive to new particles with masses of, in the units of particle physics, tera-electron volts, new masses of hundreds or even possibly thousands of tera-electron volts. The green here shows in a very crude, approximate way the masses of new particles that could have been discovered at high-energy colliders. So this is the Large Hadron Collider operating since a little after 2010. This was the Tevatron that was a predecessor. This was the SPS experiment at CERN before that. So you can see that these experiments looking for the effects of virtual particles showing up as a deformation in the shape of the electron are actually able to look for new particles with masses that are higher than what we can make directly in accelerators, and are getting better very rapidly. So I'll just point out that what we're looking for is incredibly small. The size of the deformations that we're looking for are incredibly small. So if, in order to visualize that, if we take the cloud of virtual particles that's always blinking in and out of existence around the electron, that has a certain size. And if you imagine blowing that up to the size of the Earth, and then asking how big a deformation could we have seen, the answer is we would have seen a deformation that was like taking the Earth, taking a slice 1 nanometer thick off the northern hemisphere and pasting it onto the southern hemisphere. So these are fantastically sensitive experiments, and fun but challenging. So how do we do this? Well, we use lasers to orient the spins of the electrons in the experiment. Then we apply a magnetic field that causes a torque on the magnet that the electrons carry, causes them like a gyroscope, because they're spinning magnets like a gyroscope. They rotate around due to that torque. We apply an electric field that exerts an additional torque if the electron has this deformed shape, and that causes the electrons to rotate around a little faster, or if we reverse the direction of the electric field, causes them to rotate a little more slowly. And in these experiments, basically, in order to look for a smaller and smaller deformation, you want to apply the biggest possible electric field that causes the biggest torque that causes the electrons to rotate around more or less quickly. And you want to observe your electrons for as long as possible to see how much faster they're spinning around. So the trick that we've used over the last 15 years or so in our experiment is to apply the biggest electric field by embedding our electrons inside a polar molecule. In our case, we use thorium oxide molecules. And amazingly, inside the molecule, the electron feels an electric field of about 100 billion volts per centimeter. So this would be like taking 10 billion 9-volt batteries, chaining them all together in series and connecting them on some electric field plates, some metal plates a centimeter apart. You can't actually do that. We can't afford to buy 10 billion 9-volt batteries, and even if we did, it would cause a giant spark that would explode and destroy our metal plates. But inside polar molecules, the electrons feel these gigantic fields. So our experiment we call ACME. It's a collaboration between my groups from Harvard and Northwestern University. And one of the key members of the group is Xing Wu, who's now on the faculty here at Michigan State. Let me actually skip this boring slide and go to the exciting one. If I can get it to work. Okay, I've crashed. What just happened there? It looks like my PowerPoint has crashed. That's not good. Nope. Yeah. So this, turn the music off. So this is a video showing how our experiment works to look for the electron's magnetic moment. Yeah. So the experiment uses a beam of thorium oxide molecules that travel from left to right in this picture. We create the molecules inside a cryogenic region that's cooled to about 16 degrees Kelvin, 16 degrees above absolute zero. There's a target of thorium oxide powder that we hit with a pulse laser that vaporizes the thorium oxide and creates a beam of thorium oxide molecules traveling from left to right here. The molecules interact with a series of lasers and microwaves that put the molecules into a particular quantum state. They then enter a region surrounded by magnetic shields, and with electric field plates and electric and magnetic field coils that allow us to apply electric and magnetic fields, they interact with laser beams, shown here, that polarize the direction of the electron spins in a known direction. Then the molecules travel across about 20 centimeters, where if the electron has an electric dipole moment, this asymmetric charge, it causes the electron spins to rotate. And then we detect the direction of the electron spins at the end using polarized laser light and looking at light that's scattered from the molecules into lenses that are then sent to photodetectors. So that's the ACME experiment. Here's what it looks like in real life. I've shown the dimensions on the scale of the Large Hadron Collider. So you can see this is a 1 meter long thing. We use lots of lasers, a handful of students and postdocs working on the experiment at any given time. And again, the whole thing fits in a room, maybe half the size of this room.
Oh, I want to think about, so actually this setup is right now inside this building.
Yeah, that's right. So we have a new generation of ACME, and this apparatus got moved into Xing Wu's lab for further development. So these experiments, we've been getting better and better at doing the experiments. We have friendly competitors led by Nobel Prize winner Eric Cornell, who's done even a little bit more accurate measurement than we have. But we're projecting in the next year or so to have a measurement that would see a 10 times smaller deformation than before if it's present. And these splotches of color in this plot show the predictions of different theories of what physics beyond the standard model should look like, when new particles and fields should appear and cause these deformed shape of the electron. And you can see we've already been able to rule out predictions of many different theories of what would appear beyond the standard model. But there are lots of other theories whose predictions we will only be able to test with our new experiment. So it's exciting. We never know when something might appear. So these experiments have advanced a lot in the last 15 years or so, but in some ways they still use pretty old-fashioned technology. In the meantime, the field of atomic, molecular, and optical physics has been moving very fast. And there are lots of techniques for creating ultra-cold gases of atoms and molecules that we think will make it possible to do much better experiments of this type. So, this has been a dream for a while, but now it's really a goal to do these experiments with ultra-cold gases of polar molecules trapped in traps made of laser beams, which would make it possible to have much longer observation times and see much smaller electric dipole moments. It's also sort of a dream that's now coming closer to reality, to look not just for the electric dipole moment of the electron, but also the electric dipole moment of protons or neutrons by having protons and neutrons inside exotic radioactive pear-shaped nuclei. The nucleus amplifies the effect of the proton or neutron electric dipole moment by factors of roughly 1,000 compared to ordinary nuclei. And this is something that FRIB is playing a key role in developing the techniques to be able to produce and use these pear-shaped radioactive nuclei to amplify the effects. We're going to take advantage of techniques that have been developed in atomic physics to take gases of atoms and stitch them together to form molecules while remaining at extremely low temperatures, nanokelvin, so below a millionth of a degree above absolute zero. So in the end, what we're trying to do is to make these optically trapped samples of polar molecules, funny polar molecules including pear-shaped radioactive nuclei of francium, And we're projecting really dramatic improvements in sensitivity over the next few years. So we've gotten together a collaboration of folks to work on this from various institutions with different expertise, including radiochemistry and producing ultra-cold molecules. And here's really what we're anticipating. So this plot shows, again, the mass of new particles that could be probed with these sorts of experiments through their, through their effect on nuclei via virtual particles. This is the mass that's probed already at the Large Hadron Collider, so masses below this have been explored. There's been a series of experiments over the years looking for these effects that are now already probing higher mass scales than the LHC. But we think that we're going to be able to go much further, much faster, and even, within a couple of years, we believe, probe mass scales of, within a couple of years, meaning 10 to 15 years, probe mass scales 1,000 times higher than what's possible directly at giant accelerators, which is kind of, it's extraordinary, it's exciting, and we hope that somewhere in the next, factor of 1,000 in mass, the new particles that we know must exist will appear and be visible in our experiments. So with that, I'll stop. I'll thank you for your attention, point out all the things that I've told you about are being done by an amazing group of postdocs and graduate students and undergraduates in my group. So I'll stop there and thank you.
Thank you very much, David, for a beautiful talk. Lots of really interesting physics and great explanations. So there must be questions. Questions, yeah.
So thanks for the very nice talk. In your exclusion plot for all of the theories, the air is getting thin, no? Because you have excluded many of them. So can you briefly sketch what are the ideas behind the theories that are the leftovers, or what is the hottest contender for not becoming excluded?
Yeah, so that, it's an issue because there were very strong reasons to believe that new particles would appear with a mass of around 1 tera-electron-volt. And that seems to not be how nature is. And unfortunately, there are not many reasons to know what is the scale where new things should appear now that the old expectations are wrong. So these theories that have been mostly ruled out were based on the expectation that new particles with masses of around 1 tera-electron-volt would be where the new physics is. Some of these theories are essentially saying, well, okay, we can construct less compelling, but still somewhat compelling reasons why masses would be, let's say, 10 to 100 tera-electron-volts. But really, no one knows. So, yeah, the sparseness of theories is really largely due to the fact that no one really has a good idea what the mass scale of where new particles are going to appear. So, my point of view is the right way to proceed in that situation is go as far and as fast as you can.
Yes, exactly. Yeah.
So, yeah, and unfortunately, the next collider would probably take 30 to 40 years to build, so that's not very fast.
Thank you.
Other questions?
Yeah, I'd like to come back to the idea, what you showed about you present the beta decay, so the effective Fermi interaction, and that was, which is a sort of, say, low energy tail of the W boson, and then of course it took decades to discover that. Actually, for the Z boson was a similar thing. We have first the Gargamel experiment that shows the effective interaction, and it took decades to discover the Z0. Now, it will be very compelling to say, well, that's the way how history tells us that things work for all interactions. And for example, I don't know, can we say that for the electromagnetic interaction, the classical field is first a sort of phenomenological manifestation of the photon? And do we have a similar thing for the strong interaction? Saying that,
So
I
for
mean,
the
just to say,
electromagnetic
it's super
field-
motivating because then that's, I mean, this is the way to go, so to say. First,
Yeah.
discover the low energy tail of the new particles, and then make them, yeah, show them they exist in real life. So,
Yeah, so it's actually a very interesting point, because you think about for the electromagnetic field, right? Static electromagnetic fields got Maxwell to write down Maxwell's equations. He predicted the photon, essentially. Not the photon, of course, but electromagnetic waves, which are a precursor to the photon. So yeah, it's very interesting observation. Of course, the last several decades, discovery of new particles was largely driven by colliders, the Higgs boson, the top quark.
even though, I'm sorry, the Higgs boson was, even the tail of the Higgs boson was already manifested
You're absolutely right.
in relative corrections.
That's actually right. So yeah, it's an outstanding point. You know, historically, this has been a very, very powerful way to look for the existence of new particles. Not to actually see them directly, but to see that they must exist, that the fields associated with them exist. So yeah, you know, maybe we're going back to the future. Yeah, hopefully.
Thank you.
Hopefully.
Okay. Other questions? Yeah.
For the left and right-handed coils you had, do they go around? I mean, it's the quantum realm, so it's not like it's traveling in a path like that. But does the probability cloud like loop back in on itself? Does it have to be an integer number, or does it?
No. Well, that's a good question.
Because there's a I guess there's
Yeah, so what that picture is meant to depict is, so, sorry, I know you, Gordon, so I can jump into, math language. But in quantum mechanics, you may remember that at some point you talk about probability currents. And if you have a wave function of an electron, that probability current also corresponds to an electric current. And in atoms, you can, if you have calculated the electron's wave functions, you can calculate the probability currents. And those are associated with real electric current that's flowing. And if you calculate that in the presence of Z bosons, you find that probability current has this shape.
okay.
I've never thought about whether there's some integer number of turns. Yeah, but yeah, this is what I mean by this, is if you plot out the probability currents inside an atom with weak interactions included, this is what they look like.
Thank you.
Are there other questions? Yeah, sure.
Yeah, it's probably follow up of the first question. So, talking about how is this moment search compared to the other ongoing effort in looking for dark matter, well, just fighting matter harder and harder?
So it's an interesting question, and it's a little bit apples and oranges in the sense that looking for electric dipole moments requires new forces that violate time reversal symmetry, and dark matter doesn't. So you could imagine a world where there are new particles that don't carry forces that violate time reversal symmetry, but do have the properties needed to explain dark matter. That said, in most of these theories of physics beyond the standard model, the same sorts of particles could be dark matter and could cause time reversal violating forces that would show up as electric dipole moments. And in those theories, which is not every theory, but it's a lot of theories. The sensitivity of the EDMs is actually such that it makes it hard to believe that dark matter particles of the right property are going to exist. So in certain classes of theories, these are more powerful than the dark matter searches, but there are lots of caveats and loopholes to that argument. But yeah, there are actually a couple of theoretical papers that directly make that comparison, but only a couple.
All right, other questions?
Yeah, so you said that originally there was this 1 tera electron volt scale where we were expecting a bunch of new physics and nothing so far has been found. What originally set the expectation of there being new physics there, and why now is there not a good idea of where we could see new physics, at least experimentally? Why are experimentalists now thrown off?
Yeah, fantastic question. So there were several different reasons why people thought that was where new particles would appear. One is that there was a very natural set of conditions of kinds of particles that have the properties to look like dark matter. And masses around the tera electron volt, everything sort of made sense. They had to have interactions of types that were about the right type in these theories if they had masses around the tera electron volt. It turns out that if there were lots of new particles with masses around the tera electron volt that also mediated time reversal violating forces, that altogether would have the right conditions to explain the matter-antimatter asymmetry of the universe. And then there are also some theoretical considerations. Basically, theorists think that if they didn't know about the real data of the Standard Model, they would predict that the Higgs boson mass was many orders of magnitude bigger than it's been measured to be. And in order to explain why it's not many orders of magnitude bigger, one of the simplest ways to prevent it from being so heavy is to actually have some types of new particles at the tera electron volt scale. So there are all these things that we're saying, this makes sense, this makes sense. All these mysteries would make sense if there were new particles at the tera electron volt scale. Oops. You know, what we thought made sense was wrong. So the trouble is that all of the arguments for making that, if you just say, well, what if things are 30 or 100 tera electron volts, all those arguments break. They just don't make sense anymore. Okay, maybe the problem is that what we think makes sense is wrong, that our thought process is wrong. But the trouble is that there's no new thought process that's emerged that said, oh, if everything were here, lots of things would make sense. Now it's, kind of no matter what mass scale things appear, we can't say why that makes a lot of sense. So we just have to see. Yeah.
All right, with that, let's thank David once again.